Hi, welcome back to Physics 210. Now we continue the part 2 of our physics, thermophysics. Okay, thermophysics part 2. Okay, this part 2 will be consist of 5.4. Okay, this one here. 5.4 specific heat capacity, latent heat, changes of phase, heat transfer mechanism, conduction, convection, and radiation. Okay, so we start with specific heat. Okay, there's our 5.4 yeah. Okay, specific heat. We should start. This one is under specific heat and specific heat capacity. Okay, specific heat and specific heat capacity. So first we look at what is actually the heat capacity. Okay, we look at the definition for both of them. Yeah, number one, A, that is a heat capacity. Okay, so heat capacity is big capital letter C. Okay, big capital letter C. We'll define this one first. Okay, definition first. So heat capacity is the heat needed. Okay, heat needed to raise the temperature of an object. Okay, an object by 1 degree Celsius or 1 Kelvin. Okay, so that means this big C is the total heat energy needed to raise the temperature by 1 degree Celsius. Okay, so we put this one as theta. Okay, theta or delta T. Okay, or delta T. It depends on which version you like. Alright. Now, that means we have one formula here. You know, we have Q is equal to big C delta T. Okay, so that is our equation number 1. Now the problem is heat capacity only is it is not specific. Okay, it's not really that specific because it can't tell you exactly what we want in physics actually. For example, okay, for example is this. Now let's say you have a piece of metal X. Okay, a piece of metal X. Okay, and then another piece of metal Y. Now the mass are totally different. Let's say this one is a M1 or MX and this one is MY, but we can see that from the size the MX is larger than your MY. Now let's assume you want to what we call that, you want to increase the temperature. Both of them start with the initial temperature of room temperature. Okay, so T room temperature. Now you want to increase both of them to a final temperature TF, which is much larger than the TI. So the energy needed by this guy here, or the Q on X, is equal to what? Is equal to the C. Okay, the C of the X multiplied by the changes in temperature, which is T F minus TI. And then for the Q, for the Y is CY and then TF minus TI. See or not? Well, from equation like this, it might look different. Okay, it might look different. So it starts with room temperature the same, reaching the same temperature. Now the problem is this. Now let's assume you use this formula. You want to calculate their CX and CY value. Okay, their CX and CY value. So we start with something like this. Okay, your CX is equal to QX over, let's say we call the changes in temperature is delta T, and then for the Cy is Qy over delta T. Delta T are the same for both of them. Okay, delta T are the same for both of them. Now, regardless of their mass, let's assume the amount of energy you put in. Okay, the amount of energy you put in, let's assume both, for example, your Qx is 1000 joule and your Qy is also 1000 joule. Now, that means the conclusion is your Cx is going to be the same as Cy. See or not? Even though they are totally different material and they are totally different mass. So you see that this one sometimes can be very confusing because a different material with different mass, you give them the same amount of heat and then so that their change in temperature will be the same. So that means that is not specific value. So that means it can be confused. Okay, it can be very confusing, especially when we need to determine what are those material. Okay, what are those material? So to solve this problem, we normally use a second one, which is the specific heat capacity. Okay, so specific heat capacity. Now our specific capacity have a small letter C. Okay, a small letter C, and we look at the definition first. Okay, the definition. So specific heat capacity, C is the heat energy needed to raise the temperature, okay, to raise the temperature of 1 kilogram of matter by 1 degree Celsius or 1 Kelvin. Okay, so you see that is the difference. So the difference is 1 kilogram. So you have C is equal to the heat energy needed when you try to increase temperature by 1 degree Celsius. Okay, this is 1 kilogram, is it not? 1 kilogram. So that is divide by mass, and then you divide by degree Celsius or the change in temperature. So your C is Q over M delta T, or in other words, your Q is equal to MC delta T, and which is commonly you remember as MC theta. Alright, so the difference is divide by mass. So now, when you divide by mass, now it gives you a more specific value. So you can use it to determine what type of material you are dealing with. Okay, so I'll call this one equation 1, and this one is equation number 2. Okay, equation number 2. Now look at the unit also, they are quite different. Yeah, the unit for our capacity, heat capacity only, is joule per Kelvin, and this one, small c, is joule per kilogram per Kelvin, or we can also use joule per degree Celsius. This one will be joule per kilogram per degree Celsius. They are equivalent. Okay, they're equivalent. Okay, so next one is we look at example. Okay, look at example. How do we use this formula here? Now let's assume you have this a beaker. Okay, a beaker contains water. Okay, contains water of mass, let's say 1 kilogram. Okay, water with a mass of 1 kilogram, and then at initial temperature, Ti of room temperature, let's say 30 degrees Celsius. Now calculate how much, okay, energy needed if you want this one to reach, let's say 90 degrees Celsius. Okay, so question is calculate the amount, okay, of energy needed to reach TF. Okay, TF. So the formula, because you are given mass, you are given changes in temperature. So if we look at the formula, our Q is equal to mc delta T. Now we lack of C value. Now to get the C value, you refer to your notes. This is your C value here. Okay, the C value here, this side here, for water, okay, for water in liquid form is 4186. Okay, 4186. So that value will be given here. So we calculate 1 kilogram, 4186, and then the change temperature is 90 minus 30. Changes always use a final minus initial, yeah. So we calculate our value, 90 minus 30, you should get 60, multiplied by 4186, so you get 251160 joule of energy needed to raise the temperature to that value. Okay, so that is one of the example of how to use this. Okay, how to use this one. Okay, now I have to remember our this C value. Okay, the C value is not only used for raising the temperature. You can also use it to calculate how much energy is released, okay, when the temperature drop, okay, by that much. For example, okay, yeah, this is example now, number 2. Okay, this is number 1. Now let's assume you have a beaker. Oh, I forgot to tell you. The beaker here, you're supposed to assume that it is not absorbing or releasing any heat energy, so it's a good insulator. Now let's assume you have water again. Okay, water again. Let's say now the mass is 5 kilogram. Now the initial temperature of the water, let's say, is 80 degrees Celsius. You want to put into the freezer so that the final temperature will be let's say 10 degrees Celsius, drop down by 70. Okay, so calculate how much Q is needed to be absorbed by the freezer. Okay, needed to be absorbed. Okay, needed to be absorbed. Sorry, deabsorbed. All right, so we use the same formula actually. Okay, we are using the same formula. So our Q is equal to mc delta T. The mass is 5 kilogram, 4186. Now you look carefully here. The change in temperature is 10 minus at T. See or not? So what are you gonna get? What are you gonna get? 10 minus 80 got minus 70, right? Multiply by 5, multiply by 4186. Now you get a negative number, negative 1465100 joule. Now what is that meaning when you say you have a negative sign in front? Loss. That water must lose this much energy so that the temperature will drop down from 80 to 10 degrees Celsius. You see what I mean? So that means who absorbed the energy? This one lost by this water. It will be absorbed by the freezer, okay, by the refrigerator or the freezer. So you see, using the proper convention is important. When you say changes in temperature, normally refer to final minus initial, so that you don't have the problem of determining who gained, who lost. Okay. Okay, so this is page number 1. Now, this formula, okay, we are going to use it not only in this straightforward condition, but we're going to look at 4 more examples, okay, like mixture method. Okay, mixture method. Okay, go to page number 2 now. Okay, another example. Yeah, we need to look at a lot of example. Number 3 now. Okay, this example number 3 is to mix 2 liquid. Okay, mix 2 liquid and see what happens. Let's assume you have again, this one is water. Mass is M is equal to 2 kilogram, and the temperature is equal to, let's say, room temperature 30 degrees Celsius. Now you're going to pour in, okay, you're going to pour in another beaker of water. Okay, so this one is another beaker of water, but now the mass is 1 kg and the temperature is, let's say, 80 degrees Celsius. Okay, 80 degrees Celsius. When you mix them up and calculate the final temperature, calculate the final temperature of the above mixture. Okay, of the above mixture. Now, we know that when you mix two liquids, okay, when you mix two liquids, if they are both at different temperature, what happens is the liquid at higher temperature will cool down and the liquid at lower temperature will heat up. So they finally will reach a certain temperature. So the graph will look more or less like this. Okay, let's assume we have two liquid here, right? Okay, this one is time and this one is the temperature for two different type of liquid. Let's assume the cold one, okay, let's assume the cold one start with temperature 30, right? It start with 30 here, and then the hot one start with 80, okay, degrees Celsius, sorry, okay, blue color. Now what happens is when you mix them, the temperature for the cold one will rise, okay, and at the same time the temperature for the hot one will reduce, okay, it will reduce until they reach a final temperature which are the same. Okay, now this one is the final mixture temperature, so I use a orange color. Finally they mix. Okay, so that is what happened. So you need to calculate this. Okay, you need to calculate this temperature. So this one we call the T final. Okay, the T final. Yeah. Now, to solve this type of problem, we are going to use a mixture methods. Okay, you already seen that because you already submitted your lab. Okay, now law, okay, from the law of conservation of energy. Okay, energy. We know that when someone lost, okay, when someone lost, okay, the energy, someone might gain. In that system, in that isolated system, when something lost energy, some other system must gain the energy. Okay, in this case, who lost energy? Who lost the heat energy? The hot water will lose the heat energy, and who gain? The loss will be gained by the cold water. Colder water, not to say cold water, colder water. Okay, so the formula will be the same: MC delta T, MC delta T. But I had to, because they're the same, we have to use proper subscript. This one is the hot one. Okay, so we use hot, and this one is a colder one. Okay, colder one. Okay, cold. So now because both are the same water, so we can cancel actually the C value. We cancel the C value, and now we simplify, put in what happened to the temperature there. Now this is a mass of the hot water, which is 1 kilogram, and then the change in temperature is, we know that hot water is from 80 go down to final temperature, so it will be TF minus 80. Okay, and then the cold water will have this. It starts from 30, it rises to TF, so your TF minus 30. Alright, so see, these are all value that you know except TF. So now we put in the value first, see what happens. This one is 1 kilogram, so we have TF minus 80, and this one cold water is 2 kilograms, so 2 TF minus 60. So now we put it here, we move it to the other side, we have TF only, and this one move over here. Oh, sorry, what happened to my equation? Oh, so, okay, hot one is 1 kilogram. Okay, hot one is 1 kilogram. Let's check again. Oh, sorry. Oh, this one we use what? What did I use just now? The heat. Oh yeah, because I already moved it over there, so we have to use the high minus low. Sorry, this one is high minus low. So 80 minus T final, and this one is This one is 1, so we have at T and minus TF. Okay, move together. We have 3TF is equal to at T plus this. So we have 140. Okay, divide by 3. So I have 140 divided by 3. So 46.7. 46.7 degrees Celsius. Your answer should be in between both of that extreme value, between 30 and 80. So I have that. Now another method of solving it, as I said just now, using the changes in temperature is this. This one I call method 1. Okay, method 1. Now method 2 is, remember, delta T always use a final minus that. Now the changes, okay, the energy, the changes of energy from water, hot water, the Q hot plus the Q cold must equal to 0. It must equal to 0. So we put in the formula, delta T MC delta T must equal to 0. So this one is the hot, cold. Now our hot one, because the C are the same, so we can cancel the C here, normal. Now our hot mass is 1 kilogram. This one is 2 kilogram. Now what's the change in temperature for the hot one? TF minus at T, final minus initial, plus your MC, which is final is TF minus 30 equal to 0. Okay, so now we put in the value. Hot is TF minus at T plus this one is 2. This one is also TF minus 60 now. Still 30 equal to 0. So now you open up bracket, you got 3TF. Okay, 3TF, and this one 60, so you have minus 140. So finally your temperature is still the same, 46.7 degrees Celsius. Okay, 46.7 degrees Celsius. All right. Okay, so that is a mixture method. So now, so far we assume that the container is not absorbing anything. Okay, the container is not absorbing anything. Yeah. Okay, now we want to have an example that the container is absorbing, the heat is involved. So we look at example number 4. Okay, example number 4 now. Okay, so our example number 4, let's assume you have a aluminum beaker. Okay, aluminum can. Okay, this is an aluminum can. Now, normally when the question gives you the mass of the container, then you can start believing that actually the container now is involved. Now we have two material here. This one is aluminum, okay, and let's assume it has a mass of 0.100 kilogram, 100 gram, and then this one is water. Okay, this one is water. Let's assume the mass of water is, let's say, 0.400 kilogram, 400 gram, and then their temperature. Okay, the temperature for the water is, let's say, 40 degrees Celsius, but since the water is contained by the aluminum cup, so the temperature of aluminum cup initially must be the same. Okay, so now we drop a piece of hot iron ingot. Okay, this one is let's say iron, hot iron. Now the mass of this hot iron is 0.080 kilogram, only 80 gram, and the temperature initially is, let's say, 120 degrees Celsius. Okay, 120 degrees Celsius. So the question is, calculate the final temperature of the mixture. Okay, of the mixture. All right. Now we need a few value here. Water 4186, the C value already have. Aluminum is 900. Okay, aluminum is 900. Okay, and then iron is 450. We need that later. Yeah. Okay, now first, we are going to use the law of conservation. We use method 2. Yeah, we use method 2. So we know that according to the law of conservation of energy, the energy of the iron, okay, the energy of the iron plus the energy of the water plus the energy of the aluminum must equal to 0. No way to run. Okay, no way to run. Now, formula are the same. Okay, mc delta T, mc delta T, mc delta T is equal to 0. This one is iron, this one is water, and this one is aluminum cup. Now we put in this one especially, but the C value also different, yeah. The C value also different. Okay, so now we need to calculate the final temperature. So we form equation first here. So we have mass of iron is 80 gram. Okay, 0.080. So we have 0.080, and for iron is 450. And then the temperature changes. Let's assume the final temperature is TF. So we have TF minus 120 for the iron, and then this one is plus for water is 0.4, and then multiply by 4186, and the change of temperature is final TF minus 40. And then plus again another one for aluminum can, 0.1, and then 900, and then multiply by TF minus 40, the same, equal to 0. Okay, so we simplify that number first in front before we break the column, break the bracket. So 0.08 multiplied by 450, we get 36 here. So we have 36 TF minus 120. Okay, this one again, 0.4 times 4186, we get 1674.4, and TF minus 40, and then this one is 90 TF minus 40 equal to 0. Okay, we open up the bracket. Now we have 36 TF minus 36 times 120, so now we have minus 4320 and plus 167.4 TF minus 1674.47, sorry, 0.4 only, multiply by 40, you got this 66976, and this one 90 TF. Okay, then you have 90 multiplied by 40, you got 3600 equal to 0. Now we compile, put the TF together, we have 36 and then plus 1674.4 and then plus 90. So we have 1800.4 TF is equal to everything. This one move to the other side. We have 4320 plus 66976 plus 3600. Okay, so we have 74896. Okay, we use this one, divide by 1800.4. Okay, we have final temperature of 41.6 degrees Celsius. Okay, so it's not much. Okay, the reason it is not much is because the temperature the size of the iron ingot is very small. Okay, so it's very small. So that is how we solve problem involving three metal. Okay, three metal: the iron, the water, and the aluminum cup. Okay, so that is our example 4. Now next one is our latent heat. Okay, our latent heat. But before we look at latent heat, we need to look at something called change of phase. Okay, change of phase. So this is our page 3. Okay, so that one is 5.5. Change of phase and latent heat. Okay, and latent heat. Okay, look at the first one, change of phase. Now, change of phase means physically a metal that you are studying changes its phase. So we the phase that we have here is we have gas, then we have liquid, and then we have solid. Okay, the condensed matter and the other one like plasma, we don't need that. Okay, now if we look at that process, okay, from solid, okay, from solid, when you heat it up, it will melt, become liquid. Okay, we call this process melting. Okay, melting. And then when you have liquid, heat up, it will turn into gas or vapor, and this one is called boiling. But of course we have this other name. For example, it is called vaporization. Okay, also the same, vaporization, but not what we call not evaporation. Yeah? Evaporation is at any temperature. We are talking about vaporization that is at fixed temperature or boiling temperature. Okay, now next one is the reverse. From gas, if you cool it down, it will condense to liquid, so we call that one the condensation. Okay, condensation. And then if you cool down further the liquid, this one will be freezing. Okay, freezing. Okay, so that one is a change of phase. But of course we have some other process that is directly without passing through liquid. For example, from solid, you heat it up directly, it turns into gas, like for example iodine. Okay, and that process is called sublimation. Okay, we don't calculate sublimation here because it's not a simple process. All right, so we only look at this four. Okay, now freezing has another word, is called fusion. Fusing. Okay, fusion. Okay, fusion, not the nuclear energy fusion. Yeah, we are talking about normal one, condensation, and these two process. So need to know which one absorb, which one will release the energy. Yeah. Okay, so our latent heat. Okay, that is a change of phase. Now we look at the meaning of latent heat, specific latent heat, or just called latent heat. Okay, latent heat, the symbol is L. Okay, the symbol is L, or sometimes use small l. Now we look at the specific latent heat, or just latent heat. Yeah? Latent heat is the heat energy needed to change the phase of 1 kilogram of matter at constant temperature. Okay, at constant temperature. So the L is heat energy needed. Okay, and that one 1 kilogram at constant temperature, so there is no changes in temperature, divided by mass. So our Q is equal to ml. So that is our third equation, right? The equation number 3. Step should be number 3. Number 3, equation number 3. Yeah. Okay. So, but we have two type of latent heat. Okay, two type of latent heat. So we have two type. We look at the type of latent heat. Yeah. Number 1 is latent heat of fusion. Okay, latent heat of fusion, and the symbol we use is LF. Now, what is this latent heat of fusion? Latent heat of fusion is the heat energy needed, okay, to what? Fusion have something to do with this one, right? Okay, is a heat energy needed, okay, heat energy needed to change, or the heat energy involved, not needed, it can absorb or it can release, actually involved to change the phase of matter between, okay, change the phase of matter, 1 kilogram matter, change the phase of 1 kilogram of matter between solid and liquid. Okay, so that means LF involve either from solid go to liquid or liquid go to solid. All right, and then number 2, latent heat of vaporization. Okay, vaporization, so normally LV, there is one. So our LV here is the heat energy involved to change the phase of 1 kilogram of matter, okay, between liquid and vapor or gas. Okay, between vapor or gas. So that is the 2 different things involved. Okay, so to understand more, we look at example. Okay, look at example. Yeah, example 1. Now let's assume you have okay, water. This water has a mass of, let's say, 2 kilogram at a room temperature of, let's say, 30 degrees Celsius. Okay, so now question is calculate total energy needed to boil off, okay, to boil off the water. That means you need to calculate the total amount of energy needed to actually vaporize that 2 kilogram of water starting from 30 degrees Celsius. So that means from 30 go to 100, and then from 100 it go to 100 at steam. Okay, so first thing we do here in answering this question is we draw. Okay, we draw. So see this is water, okay, liquid form, okay, water. So this one is at temperature, let's say T1, okay, temperature T1, which is 30 degrees Celsius. So you want to change this water, you want to increase temperature to 100 degrees Celsius before it can boil, right? So you need to change the water, still in water form, but now the temperature is higher, T2, 100 degrees Celsius. So here it need to absorb energy, which is MC delta T, and this one is Q1. Okay, Q1. Now if you supply energy further, the water now will start to change into vapor. Okay, it started to change into vapor. So now this is steam. Okay, steam. And of course the temperature will be the same. Okay, will be the same. And of course again it's going to absorb another type of energy, which is ML, vaporization. Okay, vaporization. So that is our diagram. So now the next part is, we know that according to the law of conservation of energy, the Q1 plus your Q2 must equal to 0. Okay, it must equal to 0. How much energy needed? Okay. Oh, sorry, we are calculating the total energy. Sorry, my mistake. This is a total energy, total. Okay, so our total energy needed is equal to Q1, MC delta T, and MLV. Okay, our mass of water, as I said, 2 kilogram, 4186 multiplied by change in temperature is 100 minus 30, and then plus 2 kilogram. Now we need the LV value. Okay, we need the LV value here. So our LV value is also given in the notes. So let's check out, yeah. Patient. Okay, LV. Okay, here, found it. Okay, this is our LV value. Heat of fusion is called heat of fusion, and this one is heat of vaporization, because this one vaporized, right? So look for water. Water is 2260. Be careful, this one is kilojoule. This one also the same, kilojoule. So 2260 kilojoule. 2260 kilo is power 3 in a unit of joule per kilogram. Okay, joule per kilogram. Okay, so we can calculate now. So 2 times 4186 times this one, the difference is 70. Okay, and then plus 2 times 2260 power 3. Okay, you need this amount, about 5 million. 5.11 10 to the power 6 joule of energy. Alright, so that is the theoretical value. Now in actual case, you might need more than this. Okay, you might need more than this. The reason is because in this calculation, we assume all the energy needed is not lost, or all the energy supplied to the water is not lost into the surrounding, and also we assume that the beaker does not absorb any energy. If the beaker absorb energy, then the energy needed here will be different. Okay, it will be different. All right, so that is our what we call it, the latent heat. Okay, example of latent heat calculation. Okay, now the next one is our heat transfer. Okay, the next one is our heat transfer. Now our heat transfer, we have 3 types of heat transfer. Okay, go to page 4 now. Okay, heat transfer, that is 5.6, the last part of part 2. Okay, heat transfer, there are 3 types of heat transfer. The first one is conduction, the second one is convection, and the third one is radiation. Okay, so first we look at the first type, A, the conduction. Okay, conduction. So conduction is when objects are in contact. Okay, when objects are in contact, that one is conduction. Okay, so for object that's in contact, for example, you have one, okay, hot object. Okay, this is a hot object. Okay, hot, and this one is cold. So what happened is, the net heat flow, remember I said net heat flow, you remember the initial or not, the previous theory, anything at higher temperature than absolute zero is going to release energy, heat energy. So even a cold one will have energy. Okay, let's say the hot one, okay, the hot one, because the temperature higher, it actually release more heat into this direction. Okay, let's say there are 2 orange color from the hot to the cold, and then you have a cold one to the hot one, is like that. Okay, so because hot object radiate more energy than the cold object, so the heat energy, the heat transfer is from the hot to the cold. Okay, this one is what we call the Q net. Okay, the net heat transfer. Okay, the net heat transfer. Yeah, so the formula that we're going to use later is the net value. Okay, it's a net value. So now heat conduction, there is a formula for conduction actually. Okay, convection and radiation we don't have at your level, you don't have, but the radiation you're going to study in another physics 310. Okay, physics 310, you're going to study that one. Okay, our heat transfer for conduction, let's assume you have hot junction here, hot junction, and then a cold junction here. Okay, this is a cold junction. Sometimes it is called reservoir. Okay, reservoir means it's a place where you can always maintain the temperature. So I call this one the hot junction, okay, the hot end. This is the hot end, and this one is the cold end. And then you have a material, okay, used to conduct the heat energy. Okay, this one is material used to conduct heat energy. So this one is a conductor normally, okay, conductor. And then to use the equation, we have to assume it must be insulated. Okay, it must be insulated. Okay, the insulation type is not important to us, but make sure it is insulated. So this one is insulated, and this one is the conductor. All right. Now, let's assume the temperature here we use is Ti, and this one is Tf. Okay. So the net heat flow is going to be in this direction. Okay. The net heat flow is in this direction. So what we want to study here is that the power, okay, the rate, okay, the rate of heat flow. Okay, the rate of heat flow, that means how much energy flow per unit time. That is a power actually. Okay, that is a power. So the symbol we use is Q over T. The rate of heat flow is given by this formula, negative K A T final minus T initial, and then divide by the length of the rod here. Okay, so this one is the length L, or you can say the distance between the hot end and the cold end. Okay, how long is a conductor? So that is our formula to calculate, okay, the rate of heat flow. Okay, the rate of heat flow, and this one is equation number 1. Okay, now what is A? We look at them one by one. Yeah, temperature you already know, the rate of heat flow you already know. Now we need two more things, K, A, and L. L is the length of conductor. Okay, and then the A is the cross-sectional area of the conductor. Okay, and then the K is what we call the coefficient of heat conductivity. Now this value is given by this chart. Okay, this chart here, we call that one the thermal conductivity or heat conductivity, coefficient of thermal conductivity, small k here. Now you have all this value. Look at this side here. This one is on kilocalorie. We look at this one. The larger the value, okay, the larger the value, the better it conduct heat. The smaller the value, the less it is able to conduct heat. That means you go above here, it is more getting better as a heat conductor. This one is getting worse as getting better as a heat insulator. Look at A, 0.023. So A is not a good heat conductor. And then you go up here, silver is much better than copper and aluminum. Okay, and of course, where is gold? Gold is not here. Gold, I think, is above here. Gold is much better. Okay, and don't be surprised, diamond up here is also a good heat conductor when it is very small in size. Okay, very small in size. So we're going to use this K value when we need to do some calculation. Okay, so now we'll look at example. Okay, look at example number 1 here. Example number 1 for this subchapter here. Now our example is like this. Yeah, so we have this. Let's assume we have a insulated rod made of aluminum. Okay, made of aluminum. Right. With a length of, let's say, 100 centimeter, and this one is made of aluminum. So aluminum, you already know aluminum is 200, right? So the K for aluminum is 200. Now what is the unit? The unit is from this one here. We know that unit is watt per meter. Okay, that will be watt per meter per Kelvin. Okay, watt per meter per Kelvin. All right. Okay. Now, the temperature here is 100 degrees Celsius, the hot end, and the cold end is 0 degrees Celsius. That means you put hot water here, boiling water or steam or hot steam, and this one is icy water. Now we know that there is a net heat flow in this direction. There is a Q. So I want to calculate the Q over T. Okay, the Q over T. Okay, so the Q, sorry, use red color, yeah. Q over T is equal to negative Ka Tf minus Ti divided by length. Okay, so now we have this negative K is 200, and then, oh sorry, cross-sectional area not given, yeah. Our A value, cross-sectional area, let's say is 200 centimeters square. Okay, so we have 200 centimeters square, but you need to use in meter square, so it's 10 to the power negative 4. And then the change temperature is 0 minus 100. Okay, so now you know why the reason I put negative sign in the equation. Okay, and then by the length of 100 cm, 1 meter. Okay, so our negative sign no more already. So now we have 200 multiplied by 200 power negative 4 multiplied again by 100 and then divide by 1. So the answer is 400 watts. Okay, 400 watt or joule per second. Okay, or joule per second. Okay, now it looks so simple to calculate, right? But there is a lot of assumption here. Okay, so one of the assumption is what? How can we simply use the equation like that? We have to assume. Okay, assumption is, okay, assumption is number one, the system reach equilibrium. That means you cannot simply put the conductor in between two and started to calculate. Cannot. You have to wait for it to reach equilibrium. Number two, the system must be insulated. Not insulated, you cannot use this to calculate because it's not uniform. Alright. Okay, so that is one example. Now next one, another example, example 2. Okay, example 2. Now let's assume in that system we have two material used. Okay, this is a hot junction, 100 degree. This is a cold junction. Now somewhere in between, okay, the lengths here. So this one have a length which are the same, 50 cm, 50 cm, but this one is aluminum, this one is copper, and this one here is a center point. Now cross-sectional area the same. The cross-sectional area is still 200 centimeters square, same. Now the question is, calculate the junction temperature. Calculate TJ, junction temperature. Junction means is the place where they meet each other. They are shoulder or they fuse together. Okay, so how do we calculate this sort of question? Okay, so assume the system, okay, reach equilibrium. Okay, reach equilibrium. When they reach equilibrium, the Q over T for aluminum side must equal to the Q over T for the copper side. See, that's it. That is the meaning of equilibrium. Everywhere should be the same. Okay, everywhere should be the here will be the same. All right. So we use the equation here, negative Ka. Okay, and then we have a temperature, right? Remember, and then divide by L. But this one for aluminum. Okay, aluminum, and this one is also aluminum. This one aluminum, and then negative K copper. Cross-sectional area the same. Temperature changes are different. This one is L copper. Okay, now put in the value. K for aluminum just now is 200, right? Okay, this value can be cancelled. Okay, can be cancelled. This one also cancelled because the length are the same. So now we have 1 here, no more already. And then this one here, changes in temperature for aluminum is what? Tj minus 100. Okay, Tj minus 100, and then is equal to negative. For copper, just now copper is 380. and then the change temperature 0 minus Tj. Alright, so now drop the negative sign. Now we have 200 Tj and then minus 20,000, and then this one is equal to 380 Tj. Okay, 380 Tj, right? Negative sign already. This one negative. So now put together, this one become 580 Tj is equal to 20,000. So our junction temperature, so answer should be in between 0 and 100. So you have 20,000 divided by 580. Okay, temperature 34.5. Okay, 34.5. All right. So there's another example on how to use this heat conduction. All right. So there is our page 3. There's our page 3 here. Okay, we go to the other two type of heat conduction. Page 4. Oh, sorry, this is page 4 already. Page 4. So the other type of heat conduction will be convection and radiation. Okay, convection and radiation. This one no calculation involved. Okay, so our first one just now is conduction. B is convection. Okay, convection is based on the movement of the mass of water. Let's start with something like boiling water in a beaker. Let's assume we enlarge the beaker here, and then we'll see what happens. Okay, now you heat up the water here. Then you heat up at the center. Normally, let's say center, you heat up. Okay, now what happens is when you heat up the mass of water at the center of the beaker, this part here become hotter when the hotter molecule are actually moving further away from each other. And when they are averagely, their average distance are further from normal, we say that they have the density decreases. When density decreases under the bulk mass of water here, this water will rise up. Then this water will rise to the top. Okay, and when they rise to the top, they get colder. Okay, they get colder, but of course not colder than the other. So what happens next is when they move up, they create a low pressure region here, and the cold water will go down and replace them. So what happened, what you see here is actually a cycle. Okay, it's a cycle. So that's what happened in conduction. So heat energy supplied at this point will be transferred to other places in the liquid, and this one is a three-dimensional process. So what happened is the energy will be distributed evenly until the temperature reach boiling temperature. That is how convection works. Okay, convection is a very complicated process. Okay, so when we look at convection, our weather system, okay, is actually based very much on convection. Okay, for example, if you look at the sea, okay, and then you have land, what happened here? When under the sunshine, okay, your water rise up, right? This one vaporize at the surface, it rise up, okay, and then it cool down, form cloud, okay, form cloud in the sky, and then condensate become heavier, and then it actually, what happened here is it actually come down as a rain. Okay, come down as a rain, and then the water run to the sea again, and the whole cycle is actually repeating over and over again for the past few millions of years, maybe billions of years. All right, so that is convection. Right, convection. All right. Okay, the next process of heat conduction, heat transfer, is radiation. Okay, radiation. Now, radiation, as I say, we only look at it qualitatively. The quantitative part you're going to learn in Physics 310, okay, under modern physics. Now, radiation from object, okay, from object. Let's say this is a piece of iron, very hot. Let's say at 700 degrees Celsius. If you touch your hand, it will be destroyed. Okay, your hand will be gone. Okay. Now, what happens is at the surface, from the surface, it will radiate infrared. Okay, it will radiate infrared in any direction, in all direction. Okay, here, 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 here. Now, any object at that temperature will radiate. Now, this is called radiation. Okay, this is called radiation. Now, what is so special about radiation? Radiation does not need any medium. Radiation, this infrared, is actually a type of electromagnetic wave. Okay, so it does not need any medium. It can actually travel through vacuum. Okay, it can travel through vacuum. So can happen in vacuum, or else the heat will not reach us from the sun. Okay, so we get the heat from the sun is through radiation. All right, so of course we can reduce the effect. For example, you want to reduce radiation, heat loss by radiation from a thermos. What do you do in a thermos? Okay, this is a thermos, right? If your thermos is like that, it actually won't do much. Okay, you can of course stop, put some insulator here. Okay, so the hot water inside there will not lose heat based on conduction. Okay, but another way to reduce that one is by putting them double layer. Okay, double layer. So why double layer? Because double layer you can actually silver them. Okay, silver them, coat them with silver. What happens is the heat, okay, no matter how, there are always some heat loss to the surrounding. Okay, but part of it will be reflected back because of the surface property. Okay, because of the surface property, not only one, two layer. Okay, two layer. So this one will reduce the heat loss to the surrounding. This one is how to reduce radiation. Okay, how to reduce radiation. All right. So these are the other two types. No calculation for this one, only for the conduction type. All right. So that's it for our chapter 5, thermal physics. Next week we are going to look at chapter number 6, gas law. Okay. Bye.